Tonight, we're going to explore something that seems impossible. Right now, as you're watching this, a machine built in the 1970s is sending signals back to Earth from over 15 billion miles away. That's Voyager 1, launched in 1977, now the most distant human-made object in existence. And here's what makes this truly extraordinary. We're still in contact with it. We're still receiving data. We're still talking to a spacecraft that's traveling through interstellar space, a realm no human technology had ever reached before. By the end of tonight, you're going to understand exactly how this works, why it shouldn't be possible with 1970s technology, and what it means that we can still hear a whisper from the edge of the solar system. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. On September 5th, 1977, a Titan Centaur rocket lifted off from Cape Canaveral, carrying Voyager 1. The spacecraft weighed roughly 1,800 pounds, about the mass of a small car. It stood about 7 feet tall, with a large dish antenna 12 feet across dominating its structure. Attached to its side was a distinctive boom extending outward, carrying scientific instruments away from the main body to reduce interference. And mounted on another boom was something remarkable for its time: a radioisotope thermoelectric generator, a small nuclear power source that would become crucial to this entire story. The mission was designed to take advantage of a rare planetary alignment, one that only occurs about once every 175 years. The outer planets, Jupiter, Saturn, Uranus, and Neptune, were positioned in such a way that a spacecraft could visit all four using gravity assists. Each planet's gravity would accelerate the spacecraft and bend its trajectory toward the next target, like a perfectly timed series of slingshots across the solar system. Voyager 1's primary mission was simpler than the full Grand Tour. Visit Jupiter and Saturn, study their moons, gather data, and then continue outward. Nobody expected it to last this long. The spacecraft was designed with a nominal mission life of 5 years, maybe 10 if everything went perfectly. That was the goal. Get to Jupiter and Saturn, collect data, send it back. Anything beyond that would be bonus. Now, it's been over 48 years, nearly a half-century of continuous operation. A machine built when computers filled entire rooms and had less processing power than a modern calculator, is still functioning in one of the most hostile environments imaginable, 15 billion miles from Earth, in interstellar space, beyond the reach of the sun's influence, in a realm where temperatures hover just above absolute zero, where radiation from cosmic rays constantly bombards the spacecraft, where the nearest star is still over 4 light-years away. And yet, every single day, Voyager sends signals back to Earth, signals so faint they seem impossible to detect. And every single day, we receive those signals. We decode them. We extract data about what Voyager is seeing in the darkness between stars. So, how is this possible? Let's start with the most fundamental question. How do we communicate with something 15 billion miles away? Let's begin with that number, because it's almost incomprehensible. Light, the fastest thing in the universe, takes about 22.5 hours to cross that distance. That means when Voyager sends a signal, it doesn't arrive at Earth for 22.5 hours. And if we send a command to Voyager, it takes 22.5 hours to get there. Round-trip communication time is 45 hours, nearly 2 days. If something goes wrong with Voyager, if an instrument fails or the spacecraft tumbles, we don't know about it for almost a full day, and our response commands don't arrive for another full day. This delay makes operating Voyager completely different from controlling a satellite in Earth orbit. With a satellite, communication is nearly instant. You send a command and get confirmation in a fraction of a second. You can adjust things in real time. With Voyager, you plan everything in advance. You send commands and then wait almost 2 days to find out if they worked. Every command sequence has to be carefully thought through because if something goes wrong, you can't react quickly. By the time you know there's a problem and send a fix, 2 days have passed. The spacecraft might have exhausted its battery backup, or drifted off course, or shut down critical systems. This forces mission controllers to be extraordinarily careful. Every command is tested and retested, simulated on ground-based computers that model Voyager's systems exactly. Only after extensive testing does a command get transmitted. And even then, there's always a moment of tension when waiting for confirmation that it worked. The answer to how we communicate begins with radio waves. Electromagnetic radiation traveling at the speed of light, about 186,000 miles per second. Voyager 1 has a radio transmitter powered by that radioisotope thermoelectric generator. The transmitter produces radio waves at a specific frequency, 8.42 gigahertz for the primary transmitter. That's 8,420,000,000 cycles per second. This radio signal is focused by the 12-foot dish antenna into a narrow beam pointed toward Earth. The beam is remarkably narrow, only about 0.5 degrees wide. That's about the width of the full moon as seen from Earth. This focusing is absolutely critical. Without it, the signal would spread out in all directions, weakening catastrophically with distance. Think about a flashlight. Shine it at a wall from 1 foot away, and you get a small, bright spot. Move to 10 feet, and the spot is bigger, but dimmer. The same amount of light is spreading over a larger area. The intensity follows an inverse square law. Double the distance, and the intensity drops to 1/4. Triple the distance, and it drops to 1/9. At 15 billion miles, without focusing, the signal would be unimaginably weak. But by concentrating the radio waves into a narrow beam, Voyager can direct most of its signal strength toward Earth. It's like the difference between shouting in all directions versus using a megaphone pointed at someone specific. Now, here's the crucial detail. The amount of power Voyager 1 has available for its radio transmitter is absurdly small. About 23 watts. That's roughly equivalent to a refrigerator light bulb. You could run Voyager's transmitter off the power adapter for a laptop, 23 watts of power focused into a beam and sent across 15 billion miles of space. By the time that signal reaches Earth, it has weakened by an almost incomprehensible amount. The inverse square law has been working against it over a distance so vast that the numbers become almost meaningless. When the signal arrives at Earth, its strength is about 0.1 quintillionth of a watt. To put this in perspective, if you could somehow collect all the radio energy that Voyager 1 has transmitted toward Earth over its entire mission, all 48 years of continuous broadcasting, and convert it to heat, you would have less energy than it takes to melt a single snowflake. That's how weak this signal is. So weak that it seems impossible to detect. And yet, we do, every day. The key to detecting such an impossibly faint signal lies in the receiving end: NASA's Deep Space Network. Three massive radio antenna complexes located roughly 120 degrees apart around Earth. One in California's Mojave Desert, near Goldstone. One in Spain, near Madrid. One in Australia, near Canberra. This spacing is not arbitrary. It was carefully chosen to ensure continuous coverage of the entire sky. As Earth rotates, different parts of the sky become visible from different locations. A spacecraft visible from California at noon might be below the horizon 6 hours later. But with stations spread evenly around the globe, at least one can always see any direction in space. For Voyager, specifically, as it's now in the southern celestial hemisphere from Earth's perspective, the Australia complex often has the best view. But all three facilities share the load. Each complex has several antennas, but the largest and most powerful are the 70-meter dishes. 70 meters is 230 feet across, about the height of a 20-story building. These are among the largest movable structures on Earth. Imagine a parabolic dish wider than 2 basketball courts placed end to end. Now imagine pointing it with such precision that it can track an object moving across the sky while compensating for Earth's rotation. That's what these antennas do, every second of every day. Each dish weighs about 8 million pounds, 9,000 tons of steel and aluminum. The reflecting surface alone weighs about 800 tons. Yet despite this enormous mass, the entire structure can rotate. It can point at any part of the sky above about 10 degrees elevation, and it can track moving objects with incredible precision. The mount is an altazimuth design. That means it has 2 axes of rotation. One vertical, allowing the dish to rotate in azimuth, sweeping across the horizon. One horizontal, allowing the dish to tilt in elevation, pointing from just above the horizon to straight overhead. Motors drive these axes. Large electric motors, each one powerful enough to rotate the entire structure smoothly. The drives are geared down dramatically. The motors spin at hundreds of revolutions per minute. But the actual dish rotation is measured in a tiny fraction of 1 degree per second. Smooth, steady, precise motion despite the enormous inertia. The pointing accuracy is extraordinary. These dishes can point to within about 0.002 degrees of their target. That's about 7 arc-seconds. Remember that an arc-second is 1/3600th of a degree. 7 arc-seconds is roughly the apparent size of a dime seen from 2 miles away. And the dish needs to maintain this pointing accuracy while tracking an object moving across the sky, while compensating for Earth's rotation, while dealing with wind loads that can push on the massive structure, while adjusting for thermal expansion as the metal heats and cools throughout the day. To achieve this, each antenna has a sophisticated control system. Encoders on each axis measure the dish position constantly, hundreds of times per second. A computer compares the actual position to the desired position calculated from the trajectory of the target spacecraft. Any discrepancy triggers a correction. The motors adjust. The dish moves fractionally. The position is measured again. The loop repeats continuously. This feedback control keeps the antenna locked onto the target, even though both the target and the Earth are moving. But pointing is only part of the challenge. The dish surface must be precisely parabolic. A perfect parabola focuses all incoming parallel rays to a single point, the focal point. If the surface deviates from a perfect parabola by more than a tiny amount, the focus degrades. Incoming radio waves don't all concentrate at the same point. Signal strength drops. The surface of each dish is made of aluminum panels. Each panel is individually adjustable. Technicians periodically measure the dish shape using laser rangefinders. They compare the actual surface to the ideal parabola. Any panel that's out of position by more than a few millimeters gets adjusted. Bolts are tightened or loosened. The panel tilts slightly. The surface comes closer to perfection. This adjustment process is ongoing. The dish structure expands and contracts with temperature changes. A 10-degree temperature swing can change the diameter by several millimeters. Wind can flex the structure slightly. Gravity itself pulls differently on the structure as it tilts to different elevations. All of these effects must be compensated for to maintain surface accuracy. Now consider what happens to the radio waves when they hit this parabolic surface. Voyager is transmitting at 8.42 gigahertz. That corresponds to a wavelength of about 3.6 centimeters, about 1.4 inches. The radio waves spread out from Voyager in all directions. The vast majority radiate off into space and will never hit anything. But a tiny fraction, the part of the beam pointed toward Earth, travels across 15 billion miles. By the time these waves reach Earth, they've spread across a vast area. The wavefront is essentially a sphere with a radius of 15 billion miles. Earth intercepts a tiny patch of this sphere. The 70-meter dish intercepts an even smaller patch. The dish has an area of about 3,850 square meters. That's roughly 41,000 square feet. About the size of a large warehouse floor. This area captures the radio waves and reflects them toward the focal point. The parabolic shape ensures that waves hitting anywhere on the dish surface all travel the same total distance to the focal point. Waves hitting the center of the dish travel straight to the focus. Waves hitting the edge of the dish reflect off the curved surface and travel a longer path. But the curve is designed so the extra path length exactly compensates. All the waves arrive at the focal point in phase. Their peaks line up, their troughs line up. They add together constructively. This focusing is what makes it possible to detect such a weak signal. Without the dish, you'd need an antenna the size of Texas to collect enough signal. With the dish, 70 meters is sufficient. At the focal point, suspended above the dish on supports, sits the feed horn. This is where the concentrated radio waves are collected. The feed horn is essentially a specially shaped metal tube, about the size of a large trash can. Its flared opening faces downward toward the dish surface. Radio waves, reflected by the dish, converge on this opening. They enter the feed horn and travel down into the receiver electronics. The feed horn is designed to match the frequency and polarization of Voyager's signal. It efficiently captures the 8.42 gigahertz radio waves while rejecting other frequencies. From the feed horn, the signal enters the low-noise amplifier. This is the critical component. The signal is so weak at this point that it's barely distinguishable from random thermal noise. Every electronic component generates noise. Electrons moving randomly in conductors create tiny voltage fluctuations. At room temperature, this noise would completely swamp Voyager's signal. So the amplifier is cooled, dramatically cooled. The current Deep Space Network receivers use helium-cooled systems. Liquid helium boils at about minus 452 degrees Fahrenheit. That's about 4 degrees above absolute zero. At this temperature, thermal motion of electrons is minimized. noise generation drops to near quantum limits. The amplifier is placed in a vacuum chamber. The chamber is cooled by liquid helium. Temperature drops to about 15 Kelvin, minus 432 degrees Fahrenheit. At this temperature, the amplifier noise is roughly 1/100th of what it would be at room temperature. That factor of 100 is the difference between detecting Voyager's signal and not detecting it. The signal enters the cooled amplifier. It's boosted by a factor of about 10 million. That sounds like a lot, but remember how weak the signal is. Even amplified 10 million times, it's still an incredibly faint signal, measured in billionths of a watt. But now, it's strong enough to be processed by room temperature electronics without being drowned in noise. From the cooled amplifier, the signal travels through cables to the receiver equipment room. This room is usually located in a building near the base of the antenna. Here, the signal is mixed with a locally generated reference signal. This converts it down from 8.42 GHz to a lower frequency that's easier to work with. It's then filtered to remove any noise outside the narrow frequency band where Voyager transmits. Digital signal processing takes over at this point. The signal is sampled thousands of times per second. Each sample is digitized, converted from an analog voltage to a digital number. Software analyzes these digital samples, looking for the patterns that indicate data. Voyager doesn't just send a steady tone. The signal is modulated. Data is encoded by shifting the frequency slightly. A shift in one direction represents a binary 0. A shift in the other direction represents a binary 1. By detecting these frequency shifts, the receiver can decode the data stream. But there's a complication: the Doppler effect. Voyager is moving away from Earth at about 38,000 miles per hour. This motion stretches the wavelength of the radio waves slightly. From Voyager's perspective, it's transmitting at exactly 8.42 GHz. But from Earth's perspective, the received frequency is lower, about 8.4199 GHz. The difference is tiny, about 100,000 Hz, but it's enough to matter. The receiver has to compensate for this Doppler shift. It has to know exactly what frequency to listen for. This requires accurate tracking of Voyager's velocity, which requires accurate knowledge of Voyager's trajectory, which requires decades of careful observation and orbit determination. The tracking is so precise that controllers know Voyager's position to within about 0.6 of a mile, out of 15 billion miles. That's an accuracy of about 1 part in 20 trillion. And they know its velocity to within about 0.04 inches per second. This precision is essential for communication. If the frequency estimate is off by too much, the receiver won't find the signal. The data rate is incredibly slow by modern standards. Currently, Voyager 1 transmits at about 160 bits per second. For comparison, a typical home internet connection is millions of bits per second. You could download what Voyager sends in 1 hour in less than 1/10 of a second on a modern connection. But speed isn't the point. Reliability is. At such low power and enormous distance, every bit of data is precious. The transmission is heavily error-corrected. Multiple copies of each piece of data are sent using mathematical codes that can detect and fix errors. If noise corrupts some bits, the error correction can reconstruct the original message. It's inefficient in terms of data rate, but it ensures that what does get through is accurate. Each station of the Deep Space Network can only see Voyager for a portion of each day. As Earth rotates, Voyager rises above the horizon at one station. The antenna tracks it across the sky for roughly 8 hours. Then, Voyager sets below the horizon. The next station picks up coverage. The handoff is carefully coordinated. Before one station loses the signal, the next station confirms acquisition. This ensures continuous contact. No gaps where Voyager is transmitting, but nobody is listening. The 3-station configuration provides redundancy too. If one station has equipment problems or weather issues, the others can compensate. During critical operations, like sending commands or receiving important data, multiple stations sometimes listen simultaneously. The signals are combined coherently. This improves the signal-to-noise ratio even further, and it provides backup in case one station loses lock on the signal. This is how we hear Voyager's whisper from 15 billion miles away. But to understand why this is remarkable, we need to understand what Voyager is, what's actually out there, sending these signals. Let's talk about the spacecraft itself. At the heart of Voyager is a computer system that would become legendary for its longevity. Voyager's onboard computer consists of 3 main units working together. The Computer Command System, or CCS, is the central processor. It handles overall spacecraft operation, executing commands, managing the spacecraft's state, coordinating all other systems. The Flight Data System, or FDS, is responsible for data handling. It collects information from the scientific instruments, collects engineering data from sensors monitoring the spacecraft's health, formats all of this into packets that can be transmitted to Earth. And the Attitude and Articulation Control System manages spacecraft orientation. It keeps the antenna pointed at Earth, controls the scan platform that points cameras and other instruments, fires thrusters when needed to maintain or change attitude. The CCS uses a custom-designed processor based on the RCA 1802 microprocessor, one of the first CMOS chips ever built. CMOS, complementary metal oxide semiconductor, was revolutionary at the time. Previous processors used bipolar transistors that consumed significant power even when idle. CMOS transistors use almost no power when not actively switching, critical for a spacecraft with limited power budget. The processor runs at about 250 kHz, 250,000 instructions per second, maximum. For perspective, that's about 10 million times slower than a modern smartphone processor. But speed wasn't the priority. Reliability was. The chip was designed to tolerate radiation. In space, high-energy particles constantly bombard electronics. Cosmic rays, protons and electrons trapped in planetary magnetospheres, solar energetic particles from solar flares. These particles can flip bits in memory, change a 0 to a 1 or vice versa. In normal computer memory, this causes errors, corrupted data, crashed programs. But the Voyager computer was designed with error detection and correction. Memory is arranged in words with extra bits for parity checking. If a bit flips, the parity check detects it. The error can be corrected if it's a single bit flip. If multiple bits flip, at least the error is detected and the affected data is flagged as invalid. The total memory available is 69,632 bytes, just under 70 kilobytes, 48 kilobytes for the CCS, about 21 kilobytes for the FDS. To put this in perspective, the text of this script is larger than Voyager's entire memory. A single second of compressed MP3 audio is about 10 times larger. One frame of HD video is about 100 times larger. And yet, Voyager runs on this amount of memory. How? Through incredibly efficient programming. The software is written in assembly language. The lowest level of programming, short of writing actual machine code in binary. Assembly language gives the programmer complete control over exactly what the processor does. Every instruction is explicit. Every byte of memory is accounted for. There's no operating system taking up memory. No background processes running. No graphical interface. Just the absolutely essential code needed to operate the spacecraft. The programmers who wrote Voyager's software had to think about every single byte. Could this variable be 8 bits instead of 16 to save space? Could these two functions share the same temporary storage if they're never called simultaneously? Could this lookup table be compressed by exploiting regularities in the data? Every optimization mattered. The result was software that fit entirely within the available memory. Software that's been running continuously for over 48 years, with updates uploaded from Earth when needed. But the core system remains based on that original 1970s code. The computer has to work autonomously for extended periods. When Voyager is out of contact with Earth, which occasionally happens during antenna maintenance or when DSN resources are allocated elsewhere, the spacecraft keeps operating on its own. It follows stored command sequences. It collects data. It monitors its own health. If something goes wrong, it has fault protection routines, automated responses to certain types of problems. For example, if the spacecraft detects that it's lost Earth lock, meaning the antenna is no longer pointed correctly, it enters a safe mode. It stops the current command sequence. It uses its star tracker to determine its orientation in space. It calculates which way Earth should be based on its internal clock and its knowledge of Earth's position. It fires thrusters to reorient. It searches for Earth's radio signal. When it finds the signal, it locks onto it. Then it waits for commands from Earth. All of this happens automatically. No human intervention required. The spacecraft can't afford to wait 45 hours for round-trip communication when there's a problem. It has to solve the problem itself. And the computer does, using logic programmed in the 1970s. With software updates uploaded over the decades to handle situations the original programmers didn't anticipate. The redundancy is remarkable too. The computer has two processing paths. If one fails, the other automatically takes over. There are two radio transmitters and two receivers, two sets of thrusters. Many components have backups that can be switched in if the primary fails. This redundancy has been essential. Over 48 years, multiple components have failed, but the backups have kept Voyager operational. Now, let's talk about power. Because this is where the story gets really interesting. Voyager 1 doesn't have solar panels. At Jupiter's distance, sunlight is already too weak for solar power to be practical. At Voyager's current distance, sunlight is almost negligible. Instead, Voyager uses 3 radioisotope thermoelectric generators, RTGs for short. These are nuclear batteries, essentially. But they're not like the batteries in your phone or car. There's no chemical reaction. No lithium ions moving between electrodes. Instead, they rely on radioactive decay, a process that will continue steadily for decades with no maintenance required. Each RTG contains about 10.9 pounds of plutonium. uranium-238. This isotope is artificially created in nuclear reactors. It doesn't exist naturally in any significant quantities. Creating it requires bombarding uranium-237 with neutrons in a reactor core. The process is complex and expensive. The plutonium-238 for Voyager's RTGs cost roughly $4 million per pound in 1970s dollars, about $110 million total in today's money, just for the fuel. This plutonium is intensely radioactive. It decays by alpha emission. Each plutonium nucleus spits out an alpha particle, a helium nucleus, and transforms into uranium-234. This happens randomly, but at a statistically predictable rate. The half-life is 87.7 years. That means after 87.7 years, half of the original plutonium has decayed. Heat output is half of what it was. Power output is half. Every time a plutonium nucleus decays, it releases energy, about 5.5 million electron volts per decay. That energy appears as kinetic energy of the alpha particle. The alpha particle is ejected at high speed, about 9,320 miles per second, about 5% the speed of light. But it doesn't travel far. Alpha particles are massive compared to other forms of radiation. They interact strongly with matter. In the RTG, the alpha particles slam into surrounding plutonium atoms within microseconds. Each collision transfers energy. The atoms vibrate faster. Temperature increases. This is how radioactive decay becomes heat. Trillions upon trillions of alpha particles per second, each one dumping its energy into the surrounding material. The plutonium is formed into pellets, small cylindrical pieces about the size of a D-cell battery. These pellets are encased in iridium. Iridium is incredibly strong and has a very high melting point, about 4,477 degrees Fahrenheit. This casing serves multiple purposes. It contains the plutonium if there's an accident during launch. A rocket explosion wouldn't scatter radioactive material because the iridium capsules are designed to survive intact. It also provides structural support and helps distribute heat evenly. The iridium-encapsulated pellets are stacked inside a graphite cylinder. Graphite serves as additional containment and as a moderator. It absorbs some radiation and converts it to heat. The entire assembly sits inside a protective outer shell, multiple layers of shielding and insulation. The outer surface of the RTG reaches about 600 degrees Fahrenheit during normal operation, hot enough to glow faintly red in complete darkness. Now, here's where the thermoelectric conversion happens. Surrounding the hot plutonium core are thermocouples, arrays of them. Hundreds of individual units working in parallel. A thermocouple is deceptively simple. Take two different metals or semiconductors. Connect them at one end to form a junction. Heat that junction. Keep the other ends cool. A voltage appears between the cool ends. This is called the Seebeck effect, discovered in 1821 by Thomas Johann Seebeck. It happens because different materials have different electron energy levels. When you heat a junction between two dissimilar materials, electrons in the hotter material gain energy. Some gain enough energy to cross into the other material. This creates a charge imbalance, more electrons on one side than the other. That imbalance is voltage. Connect a wire between the cool ends and current flows. You've converted heat directly into electricity. No moving parts. No chemical reactions. Just solid-state physics. The thermocouples in Voyager's RTGs use silicon-germanium alloys, specifically chosen for their thermoelectric properties at high temperatures. One alloy is doped with impurities to make it N-type, excess electrons available for conduction. The other alloy is doped differently to make it P-type, a shortage of electrons, or, equivalently, excess positive charge carriers called holes. When heated, electrons in the N-type material flow toward the cold end. Holes in the P-type material flow toward the cold end. This creates current in both materials flowing in the same direction through the external circuit. The hot junction is pressed against the graphite cylinder surrounding the plutonium. Temperature: there is about 1,000 degrees Fahrenheit. The cold junction extends to the outer fins of the RTG. These fins radiate heat into space. Their temperature is about 570 degrees Fahrenheit. This temperature difference, about 430 degrees Fahrenheit, drives the thermoelectric conversion. The larger the temperature difference, the more voltage is generated. The efficiency is not great by conventional power generation standards, about 6.6%. That means only 6.6% of the heat energy from plutonium decay becomes electricity. The rest, 93.4%, is waste heat radiated into space. But efficiency doesn't matter much for an RTG. The plutonium is going to decay, whether you use the heat or not. You can't turn it off. You can't save it for later. It's a constant heat source. So even 6.6% efficiency is better than nothing. And critically, it requires no maintenance, no moving parts to wear out, no batteries to recharge, no solar panels to clean. Just steady, reliable power for decades. 3 RTGs together initially produced about 470 watts of power, enough to run several scientific instruments, and the radio transmitter, and the computer systems, and the heaters that keep certain components from freezing. But here's the problem. Plutonium-238 decays. That's what makes it useful. But decay means the amount of plutonium decreases over time. And as it decreases, heat output decreases, and electrical power output decreases. Voyager 1, launched in 1977. It's now 2026. That's 48 years. About half of one half-life. The RTGs are now producing approximately 220 watts, about 47% of their original output. This is still happening. Every year, the power available decreases by about 4 watts. In 2025, Voyager had 4 watts less power than in 2024. In 2026, it will have 4 watts less than 2025. This decline is predictable and unavoidable. It's simply physics. The plutonium is decaying. There's nothing anyone can do to stop it or slow it. And this creates an impossible situation. Voyager needs power for everything. The radio transmitter to send data. The receiver to listen for commands from Earth. The computer to process data and execute commands. The gyroscopes to maintain orientation. The thrusters to adjust pointing. The heaters to keep critical systems above their minimum operating temperature. Scientific instruments to collect data. Each system requires power, and the total available power is constantly decreasing. Do the math, and you realize that eventually there simply won't be enough power to run everything. This isn't a problem you can engineer around. You can make systems more efficient. You can shut down non-essential instruments. You can reduce data transmission rates, but you can't create energy from nothing. The power is decreasing, and that's final. NASA has been managing this power crisis for decades now. It's been a constant battle against declining resources. In the early years, Voyager ran with plenty of power margin. All instruments were on. Data transmission was at maximum rate. Heaters kept everything comfortably warm. There was enough power for everything, with room to spare. But the engineers knew this wouldn't last. They could calculate exactly how the power would decline. The half-life of plutonium-238 is well established. The decay rate is predictable to many decimal places. So, they knew that by the year 2000, Voyager would have about 70% of its original power. By 2020, about 60%. By 2040, about 50%. The question wasn't whether power would decline. It was how to manage the decline, which systems to keep running, which to shut down, when to make each decision. Every choice would affect the mission's scientific return and operational lifetime. In the 1980s and 90s, the choices were relatively easy. Instruments that had completed their primary mission goals could be shut down. In 1990, after Voyager 1 completed its flyby of Saturn, the imaging system was shut down permanently. The cameras that had sent back those stunning images of Jupiter's Great Red Spot and Saturn's rings would never be used again. This decision saved about 24 watts, not because the cameras failed. They were working perfectly, but because there was nothing left to photograph. Voyager was heading out into interstellar space. Empty darkness. No planets to image. No moons. No rings. Just the occasional distant star, which ground-based telescopes could observe just as well. Keeping the cameras powered served no purpose. So they were shut off, and that power was reallocated to other systems. The scan platform, which had pointed the cameras and other instruments during planetary encounters, was also shut down. Another few watts saved. The ultraviolet spectrometer was turned off in 2003. This instrument had studied the ultraviolet emissions from Jupiter's and Saturn's atmospheres. It had discovered auroras on Jupiter, measured atmospheric composition and structure. But beyond the planets, there were few targets for UV observations. The instrument was consuming about 7 watts, power that could be better used elsewhere. The Planetary radio astronomy experiment was shut down in 2007. This instrument had detected radio emissions from Jupiter and Saturn, lightning in Jupiter's atmosphere, radio bursts associated with volcanic activity on Io. Fascinating science during the planetary encounters, but irrelevant in interstellar space, where there are no planets nearby to generate such emissions. Shutting it down saved about 5 watts. Each shutdown was carefully planned. The instrument teams had to agree that no further science would be lost. The engineering team had to verify that shutting down one system wouldn't create problems for others. Sometimes, instruments shared resources. Heater circuits, data processing, mechanical structures. Shutting down one instrument might affect another. Every dependency had to be mapped out, every consequence considered. By 2012, only 4 science instruments remained active. The magnetometer, measuring magnetic fields in interstellar space. The cosmic ray detector, measuring high-energy particles. The low-energy charged particle detector, studying the boundary between the heliosphere and interstellar space. The plasma wave instrument, detecting oscillations in the thin gas. Everything else was off. The spacecraft that once bristled with active sensors now operated on a skeleton crew of instruments. But even this wasn't enough, because power was still declining. 4 watts per year doesn't sound like much, but it accumulates. By 2015, Voyager had lost about 140 watts compared to launch. By 2020, about 170 watts. That's more than a third of the original power budget gone, and the remaining systems still needed the same amount of power they always had. The radio transmitter needed its 23 watts. The computer systems needed their power. The thrusters needed power to fire. The heaters needed power to keep components warm. Something had to give. In 2019, NASA faced a critical decision. The heaters. Many of Voyager's systems have heaters to keep them above their minimum operating temperature. In the cold of space, without heating, components can freeze. Electronics can fail when they get too cold. Semiconductor properties change. Capacitors can crack. Solder joints can become brittle. Lubricants in mechanical parts can solidify. The heaters prevent this. Small electrical heating elements wrapped around or embedded in critical components. They turn on automatically when temperature drops below a set point. Turn off when temperature rises above another set point. Simple thermostatic control. But heaters use power. A lot of power relative to what's available. The total heater power budget was about 100 watts. More than the entire science instrument suite. More than the radio transmitter. A huge fraction of available power. Shutting off heaters would free up significant power, extending the mission lifetime by years. But it would expose systems to temperatures far below their rated limits. Temperatures they were never designed to survive. Every component has a specified operating temperature range, tested during development, verified during spacecraft integration. The cameras, for example, were rated to operate down to -85 degrees Fahrenheit. Below that temperature, the mechanisms might seize up. The electronics might fail. The cosmic ray detector was rated to -59 degrees Fahrenheit. The fuel lines for the thrusters were rated to -0.4 degrees Fahrenheit. Below that, the hydrazine fuel might freeze, or the lines might clog. These weren't arbitrary limits. They were based on actual testing. Components were placed in thermal vacuum chambers. Temperature was lowered gradually. At some point, the component stopped working properly. That became the minimum operating temperature. A safety margin was added, and the final specification was set. Going below the specified temperature was entering unknown territory. It might work, it might not. There was no data, no test results, just uncertainty. The engineering team ran simulations. They calculated what would happen if various heaters were turned off, how cold each component would get, how long it would take to reach that temperature, whether there was any way to recover if something failed. They consulted with the original component manufacturers when possible. Many of the companies no longer existed, or the engineers who had designed the components had retired or passed away. The knowledge base was fragmentary. But the conclusion was clear. Turn off heaters, save power, extend the mission, but risk component failures. Or keep the heaters on, run out of power sooner, end the mission that way. NASA chose the gamble. They would start turning off heaters one by one. First, non-critical systems. Then, progressively, more essential ones. Each time, They would monitor carefully. Did the system still work at lower temperature? If yes, turn off more heating. If no, turn the heater back on. It was a delicate process. Push the limits. See what fails. Back off, just enough to keep things working. In January 2019, the first heater was shut off, the one warming the cosmic ray detector. Temperature immediately started dropping. Within a few weeks, the detector was at minus 76 degrees Fahrenheit, 17 degrees below its rated minimum. The team monitored the data stream. Was the detector still providing valid readings? Yes. The data looked normal. No anomalies. The detector kept working. Over the following months, temperature continued to drop. Minus 80 degrees. Minus 85 degrees. Minus 90 degrees. Still working. By late 2019, the cosmic ray detector was operating at minus 94 degrees Fahrenheit, 35 degrees colder than its rated minimum. And it was still functioning normally. Measurements were consistent. Data quality was good. The detector was surviving in conditions it was never tested for. Encouraged by this success, the team shut off another heater. This one, warming the fuel line for the attitude control thrusters. The line carried hydrazine from the fuel tank to the thrusters. If the fuel froze, the thrusters would stop working. Voyager would lose the ability to point its antenna at Earth. Communication would be lost, probably permanently. Because without thrusters, there would be no way to reorient the spacecraft. It was a huge risk. But the power situation demanded it. The heater was turned off in December 2019. Temperature started dropping. Slowly at first. The fuel line has thermal mass. It takes time to cool down. Over weeks, the temperature decreased. Minus 10 degrees Fahrenheit. Minus 20 degrees. Minus 30 degrees. The team watched anxiously. They tested the thrusters periodically. Brief pulses to verify they still worked. Each time, the thrusters fired normally. By early 2020, the fuel line was at minus 37 degrees Fahrenheit, 37 degrees below its rated minimum. Still no problems. The thrusters fired. The fuel flowed. No sign of freezing. As of 2024, the fuel line operates at about minus 45 degrees Fahrenheit. And the thrusters still work. This shouldn't be possible. The component was never tested at these temperatures. The specification clearly states minimum operating temperature is minus 0.4 degrees Fahrenheit. Yet, here it is, working at minus 45 degrees. 45 degrees colder than it's supposed to survive. Why does it work? Partly, conservative design. Engineers in the 1970s built things with large safety margins. Over-engineer everything. Test to one limit, but assume it might have to work at twice that limit. Design for 3 times that limit. This conservatism was cultural. Space missions were expensive and irreplaceable. If a component failed, there was no way to fix it. Better to make everything more robust than strictly necessary. And, partly, just luck. Sometimes, materials and components happen to be more resilient than expected. There's no deep reason. They just work beyond their specifications. The hydrazine might have additives that lower its freezing point more than expected. The fuel line materials might retain flexibility at colder temperatures than tested. The tolerances might be looser than necessary, allowing flow even with slight constriction from cold. Whatever the reasons, it works. And that's what matters. Because without these heaters off, Voyager would have run out of power years ago. The mission would be over. We wouldn't be receiving data from interstellar space. We wouldn't know what's out there beyond the heliopause. The science would have stopped in 2020 or 2021. Instead, it continues. Because components built in the 1970s are surviving in conditions they were never designed for. In 2023, another crisis emerged. Voyager 1's computer started sending corrupted data. The first sign of trouble came in November 2023. Engineers at the Deep Space Network received data from Voyager as usual. But when they tried to decode it, something was wrong. The data didn't make sense. Instead of readable telemetry showing spacecraft status and science measurements, they saw repeating patterns, binary ones and zeros in sequences that meant nothing. It was like the computer was stuck in a loop, outputting the same pattern over and over, not responding to the normal data collection and formatting routines. The spacecraft was clearly still alive. It was still receiving commands from Earth. The radio transmitter was working. The antenna was pointed correctly. Commands to the attitude control system executed properly. The thrusters fired when commanded. But the flight data system, the computer responsible for packaging science data and engineering telemetry for transmission, was malfunctioning. It couldn't format data properly. So, instead of useful information, Earth received gibberish. The mission team tried standard troubleshooting procedures. They sent a command to reset the flight data system, cycling the power to the affected computer. This often fixes transient software glitches, clears out corrupted memory, reloads the operating code, restarts everything from a known good state. They waited 45 hours for the round-trip communication time. The reset command traveled to Voyager. The computer rebooted. The response traveled back to Earth. When the signal arrived, the engineers examined it eagerly. Still corrupted. The same repeating pattern. The reset hadn't worked. They tried switching to the backup flight data system. Voyager has 2 of these computers. If one fails, the other can take over. Another command sent. Another 45-hour wait. The backup computer activated, but the data was still corrupted. This was alarming. Both computers showing the same problem suggested the issue wasn't a random failure. It was something systematic, something affecting both systems. The team sent diagnostic commands, instructions to the computer to run internal tests, to dump the contents of specific memory locations, to report on the status of various subsystems. Some of these commands worked. The computer would execute them and send back responses. But the responses were still corrupted, still unintelligible. For weeks, the team worked on the problem. They analyzed every bit of data they could extract, looking for patterns, clues about what might be wrong. They consulted documentation from the 1970s. Detailed schematics of the flight data system, circuit diagrams showing every connection, software listings showing every line of code. They built ground test units, copies of Voyager's computers, not identical because many of the original components were no longer manufactured, but functionally equivalent. They tried to reproduce the problem on the ground. If they could make a test unit fail in the same way, they might understand what was happening on Voyager. But the ground units worked fine. Whatever was wrong with Voyager couldn't be reproduced on Earth. December passed. January 2024. Still no progress. The spacecraft continued to function. The thrusters fired. The antenna stayed pointed. The instruments collected data, but that data couldn't be sent to Earth in usable form. Voyager was effectively blind and mute, unable to tell us what it was seeing, unable to report on its own status. Then, in late February, a breakthrough. One of the engineers noticed something in the corrupted data, a pattern. Most of the data was random, seeming ones and zeros. But, buried in that noise, was a small section that looked different. It had structure, regularities that suggested it might be actual data, just shifted in memory, located in the wrong place, as if the computer was reading from the wrong address. This clue led to a hypothesis. Maybe part of the computer's memory was corrupted, the memory that stores the code for data formatting. If that code was damaged, the computer wouldn't know how to package data correctly. It would try to execute invalid instructions, produce nonsensical output. The team went back to the schematics. They identified where the data formatting code was stored in the flight data system's memory, specific chips, specific addresses. Then they sent commands to dump that section of memory, read out the contents, send them to Earth for analysis. This process took several weeks. Memory had to be read out in small chunks, each chunk transmitted separately, each one taking 45 hours round trip. Slowly, painstakingly, they assembled a complete dump of the code memory, and there it was, a corrupted section, about 3% of the memory. In a chip that contained critical data formatting routines, the chip had failed. After 46 years in space, exposed to cosmic radiation, thermal cycling, and just age, a memory chip had died. Not completely. Most of the chip still worked, but one section, the section containing essential code, was corrupted. The data stored there was garbage. When the computer tried to execute that code, it failed. Now the team understood the problem. But understanding it and fixing it were different things. You can't replace a chip on a spacecraft 15 billion miles away. There's no repair crew, no spare parts. Whatever fix exists has to be done in software, remotely, with a 45-hour communication delay, and one chance to get it right. Because if the patch crashes the computer, the mission might be lost permanently. The solution would be to relocate the corrupted code, find somewhere else in memory to store it, somewhere that still worked. Then reconfigure the computer to use the new location. But this wasn't straightforward. The flight data system's memory was designed with specific sections for specific purposes. Code memory, data memory, scratch memory for temporary calculations. Each section had different properties, different access speeds, different protection mechanisms. You couldn't just put code anywhere. It had to go in a section that could execute code, that was accessible at the right speed, that wouldn't be overwritten by other processes. The team spent weeks analyzing the memory map, looking for available space. The problem was that the corrupted code was large, about 2,000 bytes, and most of the code memory was already full. The spacecraft's software used nearly all available space. There wasn't a contiguous block of 2,000 bytes just sitting unused, so they had to be clever. They found fragments of unused space, small gaps between other code sections, 50 bytes here, 100 bytes there, a few hundred bytes somewhere else, none of them individually large enough for the corrupted code. but together they might work. The plan was to divide the corrupted code into sections, small enough to fit in the available gaps, then write new code to tie these fragments together. A patch, essentially. Code that would call the separated fragments in the right order, make them work together, even though they were scattered across different memory locations. Writing this patch required intimate knowledge of the flight data system's architecture, how it accesses memory, how it executes code, how different sections interact. Some of the engineers working on this had been with Voyager since launch. They knew the system inside and out. Others were younger. They brought fresh perspectives, new problem-solving approaches. Together, they crafted the patch. They tested it exhaustively on the ground test units, simulated the corrupted memory, verified that the patch worked, ran it for days, looking for any edge cases that might cause problems. Only after they were absolutely confident did they prepare to upload it to Voyager. On April 18, 2024, the command was sent. 23 kilobytes of data, the new code, the reconfiguration instructions, everything needed to fix the problem. The signal traveled across 15 billion miles, 22.5 hours to reach Voyager. The spacecraft received the transmission. The computer command system processed it, verified the checksum, confirmed the data was intact, then began executing the instructions, writing the new code to memory, reconfiguring the flight data system, patching the corrupted sections. This process took time, hours on Voyager's end. Then the spacecraft had to restart the flight data system, reboot with the new configuration, and begin sending data. Back on Earth, the team waited. 45 hours total, from transmission to response. Would the patch work? Would the computer accept the new code? Would it execute properly? Or would it crash, leaving Voyager dead, unrecoverable? The waiting was excruciating. Decades of work hung in the balance. The only spacecraft in interstellar space. The only source of direct measurements from beyond the heliosphere. If this failed, that data stream would end forever. April 20, 2024. The signal came in. The Deep Space Network locked onto it, began decoding, and there it was. Clean data, readable telemetry, engineering measurements showing the status of every subsystem, science data from the 4 remaining instruments. All of it properly formatted, properly packaged. The patch had worked. For the first time in 5 months, Voyager was speaking clearly again. The control room erupted in celebration. Emails flew. Phone calls were made. The mission was saved. A computer problem, 15 billion miles away, had been diagnosed and fixed from Earth, using software uploaded across interstellar distances, with a 45-hour round-trip communication delay. On a computer designed in the early 1970s. This success speaks to the skill and dedication of the mission team. Engineers who refused to give up, who spent months analyzing data, who dug through 40-year-old documentation, who crafted an elegant solution to an impossible problem, who tested exhaustively before transmitting, and who succeeded where failure seemed inevitable. So, what has Voyager been doing all these years? What discoveries justified all this effort to keep it alive? The answer is that Voyager has transformed our understanding of the solar system and the boundary beyond. Let me take you through its journey. The mission was designed to take advantage of a rare planetary alignment. The concept of using a planet's gravity to accelerate a spacecraft had been understood theoretically since the early 20th century. But it wasn't seriously proposed for space missions until the 1960s. A jet propulsion laboratory engineer named Michael Minovich developed the mathematics in 1961 and 62, while he was a graduate student at UCLA. He was using JPL's computers to study the three-body problem in celestial mechanics, the motion of a spacecraft under the influence of two gravitating bodies like the Sun and Jupiter. While doing these calculations, Minovich realized something remarkable. A spacecraft passing close to a moving planet doesn't just fall toward it and then fly away. The planet's motion through space can add or subtract velocity from the spacecraft. If you approach the planet from behind in its orbit, relative to the Sun, the planet's gravity pulls you forward. You steal a tiny bit of the planet's orbital momentum. The planet slows down by an infinitesimal amount. You speed up by a potentially significant amount. It's like a slingshot. The planet's motion provides the energy. The gravitational field provides the mechanism, and the spacecraft gains velocity without expending any fuel. Minovich calculated that a spacecraft could visit multiple planets in sequence, gaining velocity at each one. This would allow missions to the outer solar system that would otherwise require impossibly large rockets. His work was initially met with skepticism. Some senior engineers at JPL didn't believe it could work. The numbers seemed too good to be true. But Minovich was right. The mathematics was solid, and within a few years, gravity assists were being seriously considered for deep space missions. In March 1979, Voyager 1 reached Jupiter. The spacecraft approached Jupiter at about 23,000 miles per hour relative to the planet. After the gravity assist, it left Jupiter at about 89,000 miles per hour relative to the Sun, nearly 4 times faster than when it left Earth. Jupiter itself slowed down by an utterly negligible amount. About 4/100,000ths of 1/1,000,000th of 1 inch per hour. The gravity assist also bent the trajectory, aimed the spacecraft towards Saturn. No fuel needed for this course change. Gravity did all the work. The images Voyager sent back from Jupiter were stunning. Far better than any Earth-based telescope could achieve. Jupiter's Great Red Spot, a storm larger than Earth that had been observed for centuries, was revealed in unprecedented detail. The spot is an anticyclone, a high-pressure system where winds rotate counterclockwise in the southern hemisphere. Wind speeds at the edges reach about 268 miles per hour. The storm has been raging for at least 350 years, possibly much longer. Voyager's images showed intricate structure within the spot, smaller eddies and swirls, color variations indicating different atmospheric chemistry and temperatures. The spot rotates once about every 6 Earth days, but the clouds within it have more complex motions, some regions rotating faster than others, creating shear forces that help maintain the storm's structure. Beyond the Great Red Spot, Voyager revealed Jupiter's atmosphere in stunning complexity. Dozens of smaller storms, some white ovals indicating high-altitude clouds, some brown ovals showing deeper layers of atmosphere. Band after band of clouds organized by Jupiter's rapid rotation. The planet rotates once every 9 hours, 55 minutes. This rapid spin creates powerful Coriolis forces. East-west winds reach speeds of 400 miles per hour, the fastest winds in the solar system. These winds are organized into alternating bands. Eastward flowing jets alternate with westward flowing jets. The mechanism driving these jets isn't fully understood, even today. But Voyager's observations provided crucial data for atmospheric models. Then, Voyager discovered something completely unexpected. Jupiter has a ring. Nobody knew this before. The rings of Saturn had been known for centuries, but Jupiter. Nothing in telescope observations suggested rings. Yet, there they were in Voyager's images, a faint ring of fine particles orbiting in Jupiter's equatorial plane. The ring is extremely thin, less than 20 miles thick, but it extends from about 72,400 miles to about 81,000 miles from Jupiter's center. The particles are tiny, mostly microscopic. They don't reflect much light, which is why Earth-based telescopes had never seen them. Voyager only detected them by looking back toward the Sun after passing Jupiter. The particles scattered sunlight forward, creating a bright, forward, scattered image that revealed the ring structure. The rings are probably created by meteoroid impacts on Jupiter's small inner moons. Each impact blasts particles into orbit. Most eventually fall back into the atmosphere, but impacts are frequent enough to maintain a steady population of ring particles. The moon discoveries were equally spectacular. Io, the innermost Galilean satellite, was the biggest surprise. About the size of our moon, 2,237 miles in diameter. Scientists expected a dead, cratered world like our moon. Instead, Voyager found the most geologically active body in the solar system: active volcanoes. 8 erupting volcanoes visible in Voyager's images. Plumes of sulfur and sulfur dioxide shooting hundreds of miles above the surface. Some plumes reaching heights of 190 miles. The surface was young, almost no impact craters, meaning the surface is constantly being resurfaced by volcanic activity. Lava flows, calderas, volcanic mountains. The colors were bizarre. Yellows, oranges, reds, whites, sulfur and sulfur dioxide in various forms, creating this alien palette. The volcanism is driven by tidal heating. Jupiter's gravity raises enormous tides in Io's interior. As Io orbits, these tides flex the moon. Friction from this constant flexing generates heat, enough heat to keep the interior molten, enough to drive the most intense volcanic activity in the solar system. Europa was different, a world of ice, the smoothest object in the solar system. Very few impact craters. The surface is water ice, frozen solid at the frigid temperature, about -260 degrees Fahrenheit. But the ice is crisscrossed with dark, linear features, cracks and ridges, some hundreds of miles long. These features suggested that the ice shell is relatively thin, perhaps only a few miles thick, and beneath it, liquid water, an ocean, kept liquid by tidal heating from Jupiter, not as intense as Io's heating, but enough to prevent the ocean from freezing solid. This idea that Europa might have a liquid water ocean beneath its ice shell was revolutionary. It meant Europa might be habitable, not on the surface, which is bathed in intense radiation from Jupiter, but in the ocean below, protected from radiation, with potential chemical energy from interaction between water and the rocky seafloor. Europa became one of the most intriguing targets for future exploration, and it remains so today. Multiple missions are being planned to study Europa's ocean, all because of what Voyager revealed. In November 1980, Voyager 1 reached Saturn, 20 months after Jupiter. If Jupiter was spectacular, Saturn was otherworldly. The ring system was far more complex than anyone had imagined. Telescopes from Earth had shown Saturn's rings as a few broad bands. The A ring, B ring, C ring, separated by gaps. The most famous gap, the Cassini division, separates the A and B rings. Discovered by Giovanni Cassini in 1675. But Voyager revealed that each visible ring is actually composed of thousands of narrower ringlets. The B ring alone contains hundreds of individual ringlets, each one a separate stream of particles orbiting Saturn. The ringlets aren't evenly spaced. Some are separated by clear gaps. Others are so closely packed they blend together. The structure is maintained by gravitational interactions with Saturn's moons. Shepherd moons, orbiting just inside or outside certain rings, keep the particles confined. The moon's gravity prevents particles from spreading out. Like a shepherd, keeping a flock together. Some gaps in the rings are caused by resonances. A particle in a certain orbit might complete, say, 3 orbits for every 2 orbits of a moon. This creates a periodic gravitational tug. Over time, the tugs add up. They push the particle out of that orbital zone, creating a gap. The Cassini division is caused by a resonance with Mimas, one of Saturn's moons. Voyager also discovered new rings. The F ring, a narrow ring just outside the A ring, discovered to be braided, multiple strands twisted around each other. This braiding is caused by shepherd moons, Prometheus and Pandora orbit on either side of the F ring. Their gravity creates waves in the ring, twists and kinks that propagate around the ring, creating the braided structure. All of this complexity was unexpected. The rings are made primarily of water ice, particles ranging in size from micrometers to meters, some particles as small as dust grains, others as large as houses, all orbiting Saturn in a thin disk. The rings are remarkably thin, despite their enormous diameter. The main rings extend from about 46,000 miles to 84,000 miles from Saturn's center, but they're only about 30 feet thick. If you scaled the rings to the diameter of a football field, they'd be thinner than a sheet of paper. This thinness is maintained by collisions between particles. Any particle with significant vertical motion eventually collides with others. The collisions damp out vertical motion. The result is an extraordinarily flat disk. Then Titan, Saturn's largest moon, the primary target of Voyager 1's Saturn encounter. Titan is huge, 3,200 miles in diameter, larger than the planet Mercury, and it's the only moon with a substantial atmosphere. Voyager 1 passed within about 2,500 miles of Titan's surface, much closer than the nominal flyby distance. This close approach was risky. If the calculated position of Titan was off by even a small amount, the spacecraft might impact the atmosphere, or the gravity assist might not work as planned. But the trajectory was precise. Voyager passed exactly where predicted. The atmosphere turned out to be far more substantial than expected. Surface pressure is about 1.5 times Earth's atmospheric pressure, the only other solid body in the solar system with higher surface pressure than Earth. The atmosphere is mostly nitrogen, about 95%, with methane making up most of the remaining 5%. The methane creates a thick photochemical haze. Sunlight breaks apart methane molecules in the upper atmosphere. The fragments recombine into more complex organic molecules. These molecules form a smog that completely obscures the surface. Voyager couldn't see through the haze to photograph the surface. But radar data revealed hints of what lay below, and measurements of the atmosphere provided crucial data about Titan's climate. The surface temperature is about -290 degrees Fahrenheit. At this temperature, water ice is as hard as rock, but methane can exist as liquid, solid, or gas, like water on Earth. Scientists realized Titan might have a methane cycle analogous to Earth's water cycle. Methane evaporating from lakes or seas, rising into the atmosphere, condensing into clouds, falling as methane rain, flowing in rivers back to the lakes. This idea was confirmed decades later by the Cassini mission, which discovered methane lakes and seas on Titan's surface. But Voyager provided the first evidence that Titan was a world with active meteorology, weather, driven by methane instead of water. After Saturn, Voyager 1 continued outward. Its primary mission was complete, but the spacecraft kept working, and NASA kept listening. For decades after the Saturn encounter, Voyager 1 continued outward. The scientific instruments that had studied Jupiter and Saturn were turned toward different targets. The heliosphere, the bubble of solar influence surrounding our solar system. The Sun constantly emits the solar wind, a stream of charged particles, mostly protons and electrons, flowing outward from the Sun in all directions. This wind travels at about 900,000 miles per hour near Earth, slower farther out, but still supersonic, moving faster than the speed of sound in the thin plasma of space. The solar wind carries with it the Sun's magnetic field. The field is drawn out by the flowing plasma into a spiral shape called the Parker spiral, named after physicist Eugene Parker, who predicted the solar wind's existence in 1958. This wind creates a bubble. Inside the bubble, the Sun's influence dominates. The magnetic field is the Sun's field. The particles are from the Sun. Outside the bubble is interstellar space, gas, and particles from other stars. Magnetic fields shaped by galactic processes. The boundary between these two realms is called the heliopause, and Voyager 1 was heading toward it. In 2004, Voyager 1 crossed the termination shock. This is the boundary where the solar wind slows from supersonic to subsonic. Like a shock wave in front of a supersonic jet, the solar wind, traveling faster than sound, encounters the pressure of the interstellar medium. It can't continue at supersonic speed. It has to slow down. The transition happens suddenly. A shock front where the wind speed drops, the plasma density increases, and the temperature rises dramatically. Voyager's instruments detected this transition clearly. The plasma wave instrument picked up characteristic emissions from the shock. The low-energy charged particle instrument saw the density and energy distribution of particles change. The magnetometer measured changes in magnetic field strength and direction. For the next 8 years, Voyager traveled through the heliosheath, the region between the termination shock and the heliopause. Here, the solar wind has slowed, but still dominates. The Sun's magnetic field is still the primary field, but the influence of interstellar space is increasing. The pressure from outside is compressing the heliosheath, making it narrower than it would be otherwise. Voyager's instruments monitored this region, measuring how properties changed with distance, how the solar wind weakened as Voyager moved farther out. how cosmic rays, high-energy particles, from outside the solar system became more abundant. Then, in August 2012, something changed. The low-energy charged particle instrument detected a sharp drop in solar wind particles. Over the course of just a few days, the flux of solar particles decreased by about 99%. Almost all of them disappeared. Simultaneously, the cosmic ray detector showed an increase in high-energy particles coming from interstellar space. These galactic cosmic rays had been partially blocked by the solar wind and the sun's magnetic field. Now, with the solar wind gone, they could penetrate freely. The intensity increased by about 9.3%. These changes suggested Voyager had crossed the heliopause. It had entered interstellar space. But there was confusion. The magnetic field hadn't changed direction. Theory suggested that at the heliopause, Voyager would encounter the interstellar magnetic field. This field was expected to have a different orientation than the Sun's field. Voyager's magnetometer should have detected this change, but it didn't. The field strength increased slightly, but the direction remained roughly the same. This was puzzling. Had Voyager crossed the heliopause or not? The plasma wave instrument held the answer, but it required a specific event to make a measurement. In space, the plasma wave instrument detects oscillations in the surrounding plasma, like ripples on a pond. These oscillations reveal the density of the plasma, but in the very thin plasma near the heliopause, natural oscillations are rare. The instrument mostly recorded silence. Then, in April 2013, the Sun produced a massive coronal mass ejection. A blast of plasma and magnetic field erupted from the Sun and propagated outward. When this disturbance reached Voyager's location, it caused the plasma to oscillate. The plasma wave instrument detected these oscillations. From the frequency of the oscillations, scientists could calculate the plasma density. The result was clear. The plasma density was about 40 times higher than in the heliosheath. This matched the expected density of the local interstellar medium. Voyager was definitely in interstellar space. Further analysis of the data showed that the crossing had occurred in August 2012. The particle detector had been right, but it took 9 months for the plasma wave instrument to confirm it. On September 12, 2013, NASA officially announced that Voyager 1 had become the first human-made object to enter interstellar space. After 36 years of travel and over 11 billion miles, it had left the heliosphere behind. The magnetic field mystery took longer to solve. It turned out that the interstellar magnetic field in the local region happens to be oriented in roughly the same direction as the Sun's field, just by chance. This made the transition less obvious. But detailed analysis of the field's strength and structure confirmed that Voyager was indeed in a different magnetic environment. The interstellar field compressed against the heliosphere, creating a complex boundary layer. Voyager had crossed through this layer into true interstellar space. So, what's it like out there? What is Voyager discovering in this alien realm? The interstellar medium is a near-perfect vacuum by Earth standards. About 0.09 atoms per cubic centimeter in Voyager's current location. That's about 90 million trillion times less dense than Earth's atmosphere at sea level. You could fit all the matter in a cube of interstellar space 1,000 miles on a side, and it would weigh about as much as a small car. The particles are mostly hydrogen, about 90% by number, with helium making up most of the remaining 10%. These atoms are incredibly cold, about -457 degrees Fahrenheit, just 16 degrees above absolute zero. At this temperature, atoms barely move. Thermal velocities are just a few hundred feet per second. But superimposed on this cold background are much hotter particles, cosmic rays, protons, and heavier nuclei accelerated to near light speed by supernova explosions and other violent events. These particles have energies ranging from millions to billions of electron volts. For comparison, the particles in Earth's atmosphere have thermal energies of about 0.025 electron volts. Cosmic rays are billions of times more energetic. When a cosmic ray particle enters Voyager's cosmic ray detector, it ionizes atoms along its path. The resulting electrical signal reveals the particle's energy and sometimes its type. Voyager's measurements show that cosmic ray intensity varies, not just with distance from the Sun, but also with time. The Sun's activity follows an 11-year cycle. During solar maximum, the Sun's magnetic field is stronger and more tangled. This field partially blocks cosmic rays from entering the heliosphere. Cosmic ray intensity at Voyager's distance decreases. During solar minimum, the Sun's field is weaker. Cosmic rays penetrate more easily. Intensity increases. By monitoring these variations, scientists can learn about both the Sun's influence and the properties of the local interstellar medium. The plasma wave instrument has made some of the most surprising discoveries. In 2012 and 2013, it detected oscillations in the plasma. These weren't random fluctuations. They were organized waves, like sound waves, but propagating through plasma instead of air. The frequency of these waves is related to the plasma density. Higher density produces higher frequency oscillations. From 2012 to 2015, the measured frequency gradually increased. This means the plasma density was increasing. Voyager was moving through a region where interstellar space was getting slightly denser. The density rose from about 0.06 electrons per cubic centimeter to about 0.12 electrons per cubic centimeter. Still incredibly diffuse, but measurably denser. This gradient suggests that the local interstellar medium isn't uniform. There are density variations, possibly related to the local interstellar cloud, a region of slightly higher density that the solar system is currently passing through. In late 2020, the plasma wave instrument detected something new, a persistent, faint hum, a continuous emission at frequencies around 2 to 3 kilohertz. This emission comes from thermal motions of electrons in the plasma. It's like hearing the thermal vibration of the medium itself. The fact that this emission is detectable means the plasma is slightly warmer and denser than the very cold, diffuse gas between clouds. Voyager is traveling through the boundary of the local interstellar cloud, a region where multiple clouds of gas and dust overlap, creating complex structure in density and temperature. The magnetometer continues to measure magnetic field, strength, and direction. The interstellar magnetic field in Voyager's current location is about 0.4 nanotesla. That's 4/10 of a Tesla. For comparison, Earth's magnetic field at the surface is about 50,000 nanotesla, over 100,000 times stronger. But even this faint field is significant. It affects how charged particles move. It shapes the structure of the interstellar medium. It connects to the larger scale magnetic field of the galaxy. The field direction varies slowly as Voyager moves, sometimes pointing north, sometimes south. These variations reveal the structure of magnetic field lines in the local region, how they drape around the heliosphere, how they connect to fields from other stars and from the galactic disk. The fact that Voyager is still functioning in interstellar space is remarkable. This environment is different from anything it was designed for. The radiation environment is dominated by galactic cosmic rays instead of solar particles. The temperature is colder. The plasma density is different. Yet, the spacecraft keeps working. The instruments keep taking data. The computer keeps processing it. The radio keeps transmitting. Every day, Voyager sends back measurements. Data that no other spacecraft can provide. Data that's rewriting our understanding of the boundary between the solar system and the galaxy. But time is running out. The power budget is unsustainable. Currently, Voyager 1 generates about 250 watts. It uses, essentially, all of it. Every year, 4 watts disappear. By 2030, NASA estimates they'll have to start shutting down science instruments. Not because of failure, simply because there won't be enough power to run them. The magnetometer might be the first to go. Then, the cosmic ray detector. One by one, the instruments will be turned off to conserve power for essential systems. By 2036, possibly earlier, all science instruments will be off. At that point, Voyager will still have power for the radio transmitter and receiver, for the computer, for the thrusters that maintain pointing. But it won't be collecting data. It will just be sending a carrier signal. A tone that says, "I'm still here." That could continue for a few more years. But eventually, even that will stop. The power will drop below the minimum needed to run the transmitter. The signal will fade, and then silence. NASA estimates this will happen sometime around 2036, maybe as late as 2040, if they can squeeze out a few more years through clever power management. But the end is coming. It's inevitable. Plutonium decays. Power decreases. And eventually, there's just not enough to continue. When Voyager 1 finally goes silent, it will keep moving. It's traveling at about 38,000 miles per hour relative to the Sun. That velocity will not change significantly. There's nothing in interstellar space to slow it down. No air resistance. No gravity from nearby planets. Just emptiness. It will coast on essentially the same trajectory forever. In about 40,000 years, Voyager 1 will pass within about 1.6 light-years of a star called Gliese 445. That's close in interstellar terms, though still vastly far by human standards. About 10 trillion miles. Voyager will make this passage in silence. No radio transmitter. No instruments recording the moment. Just a dead machine drifting past a distant star. After that, it will continue wandering through the galaxy. Perhaps in a few million years, it might pass near another star system. Or it might drift through empty space for billions of years without coming close to anything. There's no way to predict its path that far into the future. Too many gravitational influences from passing stars. Too much chaos in the motion of the galaxy itself. But somewhere out there, it will be. A tiny capsule of human engineering, silent and dark, carrying a golden record with sounds and images from Earth. A message from a civilization that might not exist anymore by the time anyone finds it. Attached to the side of Voyager is a golden phonograph record, 12 inches in diameter, gold-plated copper, containing sounds and images from Earth, a message in a bottle cast into the cosmic ocean. The record was Carl Sagan's idea primarily. Sagan was an astronomer and science communicator who served on the Voyager science team. He understood that Voyager would eventually leave the solar system entirely. It would drift through interstellar space, essentially forever. And there was a tiny, infinitesimal chance that someday, billions of years in the future, it might be found by another civilization. So why not include a message? The record contains 116 images, photographs and diagrams showing scenes from Earth, mathematical and physical principles, the structure of DNA, human anatomy, pictures of people from different cultures, landscapes, cities, animals, plants. It contains 90 minutes of music, works from different cultures and time periods. Bach, Beethoven, Mozart, traditional music from China, India, Peru, Zaire, Chuck Berry's Johnny B. Good, blues, jazz, rock and roll. And it contains spoken greetings in 55 languages. From Sumerian, a language dead for thousands of years, to modern languages like English and Mandarin. Each greeting is brief, just a sentence or two. Hello, from the children of planet Earth. Encoded on the record are also natural sounds: wind, rain, thunder, surf, earthquakes, volcanoes, birds, whales, elephants, human sounds too, footsteps, heartbeats, laughter, the sound of a mother and child, and one final addition: brainwaves. Anne Druyan, a member of the record team and Sagan's future wife, had her brain activity recorded for an hour while she meditated on various thoughts and emotions about Earth, life, and the human experience. Those brainwaves were encoded onto the record, a snapshot of human consciousness, preserved in gold, traveling through the void. The record comes with a cartridge and stylus. Instructions for playing it are etched onto the cover, diagrams showing how to extract images and sound from the grooves, a pulsar map indicating Earth's location relative to 14 pulsars. The locations of these pulsars and their rotation periods would, in theory, allow an advanced civilization to determine where and when the record came from. Of course, the chances of anyone ever finding Voyager are essentially zero. Space is incomprehensibly vast. Even traveling through our relatively dense galactic neighborhood, Voyager could drift for billions of years without passing close to another star system. And even if it did pass near a star, the odds of anyone noticing it are vanishingly small. It's a tiny object, silent and dark, indistinguishable from a small asteroid, unless you look very closely. But that wasn't really the point. The golden record wasn't primarily for aliens, it was for us. A reminder of what humanity can be. A collection of our best qualities. Our art, our science, our diversity, our wonder, preserved in a form that could theoretically last billions of years. Long after our civilization is gone. Long after Earth itself might be gone. The record will remain, drifting through the galaxy. A testament that we were here, that we thought about our place in the cosmos, that we reached out into the darkness, not knowing if anyone would ever answer. The fact that we're still in contact with Voyager 1 is remarkable on multiple levels. First, the engineering. This spacecraft was designed before microprocessors were common, before compact disc players, before pocket calculators were widespread. Engineers in the 1970s built this machine with the tools and technology they had available. And they built it so well that it's still working nearly 50 years later. In an environment it was never expected to survive in. That's astonishing. Second, the operations. Maintaining contact with Voyager requires incredible precision. The Deep Space Network antennas must track a moving target billions of miles away. Commands must be carefully planned and tested because there's no room for error at 45-hour round-trip times. Power must be meticulously managed as available resources dwindle. Every decision could be the one that ends the mission. Yet the team keeps it going, year after year, solving problems that arise, adapting to declining power, squeezing out every last bit of operational life. Third, the science. Voyager is returning data from a realm humans had only theorized about, interstellar space. The galaxy beyond the sun's influence. The observations it's making are unique. No other spacecraft can provide them, at least not yet. Other missions like Voyager 2 and New Horizons may eventually reach interstellar space, but that's years or decades away. For now, Voyager 1 is alone out there, the sole representative of humanity in the vast darkness between stars. And we're still listening to it, still receiving its faint whisper, still decoding the message it sends across billions of miles. When you think about radio communication across interstellar distances, Voyager is just the beginning, a proof of concept. 23 watts of power, a 12-foot antenna, and signals that cross 15 billion miles. If we can do that with 1970s technology, what might be possible with modern technology or future technology? Radio telescopes have improved dramatically since the 1970s. The Allen Telescope Array, the 500-meter aperture spherical telescope in China, the square-kilometer array under construction. These instruments are orders of magnitude more sensitive than anything available when Voyager launched. They could detect even fainter signals from even greater distances. If a civilization around another star were broadcasting with power comparable to Voyager, we might be able to hear them. If they're broadcasting with more power, say kilowatts or megawatts instead of watts, we definitely could. The same physics that lets us talk to Voyager could let us talk to someone else, somewhere else, if they're out there, if they're broadcasting. This is part of why the search for extraterrestrial intelligence matters. We know radio communication across vast distances is possible. We're doing it right now, every day, with Voyager. The question is whether anyone else is doing it too. Consider what we've accomplished. In 1977, we launched a spacecraft, aimed it at Jupiter and Saturn, equipped it with cameras and sensors and a radio, powered it with nuclear batteries that would last for decades, and sent it on a trajectory that would carry it out of the solar system entirely. That spacecraft is now 15 billion miles away, farther from Earth than any human artifact has ever traveled, and we're still talking to it. We're still getting data, still sending commands, still maintaining a connection across a gulf so vast that light itself takes nearly a full day to cross it. This connection is fragile. It depends on the plutonium continuing to decay and produce heat, on the RTGs continuing to convert that heat to electricity, on the radio transmitter continuing to function, on the antenna continuing to point toward Earth, on the Deep Space Network continuing to listen, on engineers continuing to manage declining power and solve problems as they arise. Any one of these could fail. And when it does, the connection will be lost, probably forever. But for now, in this moment, it exists. A thread of radio waves connecting us to the edge of known space. A machine from the past, still speaking to us, still telling us what it sees, still carrying out its mission decades after that mission was supposed to end. The story of Voyager 1 is a story about human persistence, about solving problems, about making things work even when they shouldn't, about pushing the limits of what's possible. It's easy to take this for granted, to see the headlines that Voyager is still operating and think of course it is. But there's nothing of course about it. Every year that Voyager survives is a triumph of engineering and operations. Every watt of power carefully allocated. Every instrument shut down, thoughtfully planned. Every command sequence meticulously tested. Every crisis troubleshot and resolved. The team operating Voyager has been doing this for decades. Some have been with the mission since launch. Others joined later. But they all share a commitment to keeping this spacecraft alive, to extracting every last piece of data, to maintaining contact as long as physically possible. They know it can't last forever. They know the power will eventually run out. They know silence is coming, but they're not there yet. And until they are, they'll keep listening. Keep talking. Keep working. There's something profound about this, about the fact that we're still connected to Voyager, still hearing from it. It speaks to what humans can do when we try, when we build things to last, when we plan for the long term, when we solve problems instead of giving up. Voyager 1 was built to visit Jupiter and Saturn, to operate for 5 years, maybe 10. It's been 48 years. It visited Jupiter and Saturn and then kept going, into the outer solar system, past the edge of the sun's influence, into interstellar space. And it's still working, still sending data, still functioning in an environment it was never designed for. That's not just engineering. That's persistence. Human stubbornness applied to exploring the cosmos. The determination to see what's out there, to go farther, to learn more, to push the boundaries of what we know. When the signal finally stops, when Voyager falls silent, it will mark the end of an era, the end of the first interstellar mission, the end of the longest-running spacecraft mission in history, the end of our connection to this particular piece of human history. But it won't be the end of exploration. Other spacecraft are coming. Voyager 2 is still operational, following behind Voyager 1 by a few years. New Horizons, which flew past Pluto in 2015, is heading outward. It might reach interstellar space in the 2040s if it survives that long. And future missions will go farther, with better instruments, more power, faster communication. Each building on what Voyager taught us, each pushing a little farther into the unknown. Because that's what we do. We explore. We build machines to go where we can't. We listen to their faint whispers from the darkness. We decode their messages. We learn. And then we build the next one. Send it a little farther. Listen a little longer. Learn a little more. So when you think about Voyager 1, think about what it represents. A machine built in the 1970s that's still working in 2026. A radio signal crossing 15 billion miles. A power source declining by 4 watts per year, but still sufficient. A team of engineers and scientists managing an impossible situation. A connection to interstellar space maintained against all odds. It's improbable. It's extraordinary. And it's real. Right now, as you're reading this, Voyager is out there, transmitting, sending data, telling us what it sees in the darkness between stars. And somewhere on Earth, a massive antenna is listening, receiving that impossibly faint signal, decoding it, delivering it to scientists who study it, who learn from it, who add it to humanity's knowledge of the universe. That's the miracle, not that we built Voyager. Lots of spacecraft have been built, not that we launched it. Lots of spacecraft have been launched. The miracle is that we're still talking to it, still connected, still learning. Across a distance so vast, it strains comprehension. With technology so old, it predates most of the people operating it. Against odds that say it shouldn't be possible, we're doing it. Every day. And we'll keep doing it until the power runs out. Until the plutonium can't generate enough heat. Until the last watt is consumed. Until the transmitter falls silent. Until the connection is finally, inevitably, lost. But we're not there yet. And that's something worth thinking about. Thanks for staying with me through this journey to the edge of the solar system and beyond. The signal from Voyager 1 is still out there, still reaching across the void. And for as long as it keeps transmitting, we'll keep listening.